Last week we have started the topic on vibrational spectroscopy. Now we continue with this. For the determinations of vibrational energy level, we first presume that the molecule vibrate harmonically, where the potential energy curve is similar to the quadratic curve. However, due to some reasons whereby as the molecule with the atom is approaching each other, and when the atoms are very far apart, the effects of the energy is not being considered in the harmonic oscillators. So it comes in with the enharmonicity, which it applied the Morse potential energy curve to explain the potential energy of a molecule. With the applications of this enharmonicity, then it breaks down the selection rules for the transitions, whereby the change of the vibrational quantum level is no longer restricted to increase by one level upon the absorptions or the activations of the molecule from one level to another level. So for the selection rules in these enharmonic oscillators, the change of the vibrational quantum level during the excitations can be any level, meaning that the molecule can be excited to more than one level compared to their initial state. Therefore, we have the delta vibrational quantum level is equals to +2, +3, or many more. The higher vibrational transitions are allowed in the enharmonic oscillators, but we will observe that if the transitions involve the higher energy levels, then the appearance of the spectral lines in the spectrum, it will show a very low intensity. The reason is allowed these transitions more than one level is due to the energy levels is getting closer as the vibrational quantum number increases. So due to these selection rules where you can have more than one change of the vibrational quantum number upon the excitations, then we will be able to observe more than one peak to be appear in the spectrum. With the applications of the enharmonicity and the change of the selections rules which allow more than one level, then it will cause the transitions, for example, for a molecule to transit from the ground state to the first excited state, or from the ground state to the second excited state, or from the ground state to the third excited state. And the transitions from ground state to first excited state is known as the fundamental transitions, whereby the transitions from the ground state to the second excited state is known as the first overtone. The change of the vibrational quantum number is +2. In addition to that, there is also the possibilities whereby the transitions can occur from the ground state V0 to V3. So the delta V will be +3, which is known as the second overtone transitions. So from here you will see that the fundamental transitions will result in the highest intensity peak in the spectrum, whereby for the transitions involve the overtone, the intensity of the peak will be much more lower. So the transitions where the delta V is greater than 1 is known as the overtone bands in the spectrum. Therefore, you have the first overtone and second overtone because of the enharmonicity oscillators assumption. And where are the positions of these fundamental transitions, first overtone, second overtone, to be observed in the IR spectrum? Figure here shows the cost structure of the infrared spectrum for HCl. There are two things that we need to look into. for the spectrum. Number one is the intensity of this spectral line, which is indicated by the height of the spectral line. The next one is the positions for each of these peaks. If we look into the intensity of the spectral line, we observe that the intensity decreasing, where the first line has the highest intensity, and it is represent the transitions from V0 to V1. The next line, which is lower intensity compared to the first line here, it is due to the transitions from V0 to V2, whereby this line is dedicated to the transitions from V0 to V3, which means that as the transitions involve the change of vibrational quantum number with higher value, then the intensity of the peak will be decreasing. Now, we have to look into what is the reason that caused the reductions of the intensity. When we talk about intensity of the spectral line, then we have to relate it to the populations of the molecule at the initial state, and also the energy gap between the transitions. Okay, for the first line here, which is due to the fundamental transitions, meaning that the molecule transits from the ground state to the first excited state, the energy required for these transitions is just this amount. While for the transitions involve the overtone, where it starts from V0 to V2. Okay, so these transitions require higher amount of energy to occur compared to the fundamental transitions, whereby the second overtone require even higher amount of energy to occur compared to the first overtone and also the fundamental transitions. As the amount of energy required is getting large, if the delta V involved is high, then the molecule which has this sufficient amount of energy to conduct the excitations will be less. That is the reason why usually the fundamental transitions will result in a very intense peak, because usually the molecule can gain easily this amount of energy for the activations to occur. But in order to result in the first overtone transitions, the molecule needs to gain more energy from the light source, and not so much of molecule compared to the fundamental transitions that can transit from the V0 to V1, because the amount of energy required is much more higher compared to the fundamental transitions. Therefore, the intensity of the peak for the first overtone will be lower compared to the fundamental transition. Not to say the second overtone. For the second overtone to occur, the molecule needs to absorb this amount of energy from the light source. And this is quite a large amount of energy, and not many molecules manage to achieve this amount of energy. Therefore, only a few of them will have the chances to transit from V0 to V3. As a result, you will see that as the transitions involve large delta V, then the intensity of the peak will become lower and lower. We have looked into the intensity variation in the IR spectrum. Now, what about the position of the spectral line for the fundamental transition, for the first overtone, and also the second overtone? We use these equations to determine the energy for each vibrational quantum level. In order for the transitions to occur, the molecule must be excited from one level to another level. So we have to find out the energy difference for the molecule. where this is the amount of the energy that the molecule needs to absorb in order for the transitions to occur from the initial state to the final state. Okay, so if you substitute this with V and also V plus 1, the final equations you will get for delta G is these equations. Okay, so for transitions which involve delta V equals to 1, which is referring to the fundamental transitions from V0 to V1, the amount of the energy required is this. Whereby for the first overtone with delta V equals to 2, where the molecule transits from V0 to V2, this is the amount of the energy that the molecule needs to absorb from the light source. And similarly, for the second overtone, here is the equations to determine the amount of the energy that the molecule needs to absorb from the light source. Chi E is the anharmonicity constant. This value is about 0.01. If you compare the delta V for each of these transitions, fundamental transitions, first overtone and second overtone, you will observe that each of them, okay, for the first overtone is about double of the fundamental transitions, whereby the second overtone is about triple the fundamental transitions. So this amount of energy that the molecule needs to absorb, it is the positions on the x-axis in the spectrum. Therefore, you will see that the distance between the fundamental transitions and the first overtone is about double. Then for the second overtone, the positions for the second overtone is about triple of the value for the fundamental transitions. This is one of the example to determine the force constant for the HCl bond. If you were given the spectrum and this spectrum shows the peak at different positions. So you have to find out what is the difference between each of these peak, and then you have to know that in fact one of the peak is the fundamental transitions and the next one is the first overtone, then this one is the second overtone, whereby they are different compared to the fundamental transitions with the frequency or the wave number, which is 2 times and also the 3 times much higher for the overtones compared to the fundamental transition. So you have to find out what is the hypothetical vibrational frequency or the hypothetical equilibrium oscillation frequency, omega E, and then the chi E, which is the anharmonicity constant, by solve the equations here simultaneously. Then from here, you will be able to find out what is the force constant for the bond between the hydrogen and also the chlorine atom. So for sure, you have to calculate what is the reduced mass for HCl. For the fundamental transitions and also the overtone, the initial state of the molecule is at the ground state. Now we are looking for another type of the transitions, which is known as the hot bands. Hot bands involve the transitions of the molecule from the first excited vibrational energy level, vibrational quantum number equals to 1 or higher. For this kind of transitions, the intensity of the peak is very low and it is usually not observable at room temperature, meaning that if you conduct the experiment at room temperature, you will not be able to observe the appearance of this peak in the spectrum. But if you change the conditions of the experiment to a higher temperature, then you will realize that in the spectrum there is an additional peak, and this peak the intensity is not very high. It has a very weak intensity. So this peak is due to the transitions of the molecule from the first excited state to a second excited state, or for the transitions from second excited state to third excited state. So this band, we call it as the hot bands. Now it comes to the questions, why the hot band will only be observed in the spectrum when the temperature of the experiment increase. Before we move into the details on these explanations, let's look into this vibrational energy and also the distributions of the molecule in the vibrational energy level. For most vibrations, the separation between the energy level, the delta E, is very much greater than the thermal energy of the molecule. Therefore, most of the populations will reside in the ground vibrational energy level. We can also show this or prove this through the mathematical expressions for the ratio of molecular populations at ground state compared to the excited state. So in this ratio here, we have the number of molecule at the final state or the excited state to the number of molecule at the initial state or the ground state. And this ratio of the populations is proportional to the exponent of negative delta E, the energy difference between the two levels, to the thermal energy of the molecule. And because the delta E is very big, therefore the exponent value will be very small. If this is very small, which means that most of the molecule that are participating in the initial state or at the ground state, because this value is large, only then we can get a small value here. And the value or the number of molecule at the excited state will be low. Okay. We can apply the equations for the ratio of the molecule at the excited state to the ground state in solving this problem, where you are asked to determine the population ratio between the level V equals to 1 and V equals to 0 by assuming that the separation between the energy level is about 1000 wave number at 25 degrees Celsius. The number of molecule at the excited state n1 to the number of molecule at the ground state n0 is equals to exponent minus delta E divided by the thermal energy kT. So since the questions give you the wave number for these energy separations, we have to convert this wave number into joule by multiply the wave number with the Planck constant and the speed of light. We have to take note that the speed of light needs to be converted to have the unit that is consistent with the wave number. Therefore, we have the speed of light equals to 3 times 10 to the power of 10 divided by the Boltzmann constant, multiply the temperature in the units of Kelvin. So after you do some calculations, then you will find that the ratio of the molecule at the excited state to the ground state is equals to 0.01. According to the Boltzmann equations, the populations of states at V equals to 1 is 0.01 or 1% of the ground state. Therefore, we may ignore all the transitions from V equals to 1 and upper at room temperature because there is limited number of molecules which can perform the transitions from V1 to V2 and show us the hot band in the spectrum. If the temperature is raised or if the vibration has a particularly low frequency, meaning that if the energy required for the transitions to occur is become less, then the populations of the excited state may become appreciable. For example, if the conditions of the experiment is changed to a temperature of 600 Kelvin, then the number of population ratio at the first excited state to the ground state will become about 0.09, which is close to 10% of the molecule from the ground state will be occupying the first excited state. And this will allow the molecule from the first excited state to transit to the second excited state upon absorption of sufficient energy from the light source, and cause the appearance of the spectral line known as hot band in the IR spectrum. So a similar increase in the excited state populations can also be arise if the vibrational frequency were about 500 wave number instead of 1000 wave number, which is related to the delta E. Okay, if the delta E is smaller, then the chances for the molecule to occupy the excited state will be higher, and it will proceed with the transitions to the higher excited state. As a summary, as the temperature increases, the populations of the excited vibrational state will increase. The number of molecules at the excited state will be increased. Therefore, the intensity of the hot band will increase. But at the same time, the intensity of the fundamental will decrease as the temperature increases. Why the fundamental peak will decrease in the intensity? The reason is that the molecule from the ground state has been transit to the first excited state upon the increase of temperature. So the number of molecules at the ground state is decreasing if the temperature of the experiment is raised. Therefore, the molecule which will do the transitions from V0 to V1 will also become less compared to if you conduct the experiment at room temperature, which has more number of molecules at the ground state. While for the overtone, the initial state is always the V equals to 0, which is the ground state. The intensity of the overtone will also be decreased as you increase the temperature of the experiment with the same explanations as the fundamental transitions. So where is the positions of the spectral line for the hot band transitions? When we compare the fundamental transitions, first overtone and second overtone, their positions is about 2 times for the first overtone compared to the fundamental transitions, and 3 times compared to the fundamental transitions for the second overtone. But for the hot band transitions, the positions of the peak is at the left-hand side compared to the fundamental transitions, which means that the amount of the energy required for the hot band to occur, for the transitions from V1 to V2 to occur, is required less amount of energy compared to the fundamental transitions. The drawing here visualizes the energy gap between the ground vibrational energy level, first excited vibrational energy level, second excited vibrational energy level, and so on. So these are the equations that we use to determine the value of energy for each level. And here are the energy required from the light source in order to activate the molecule from ground state to first excited state, and from the first excited state to the second excited state, which is the hot band. If you compare these two, you will realize that the fundamental transitions has to minus 2 times the hypothetical vibrational frequency and also the enharmonicity constant, whereby for the hot band to occur, the amount of energy difference is minus 4 times the hypothetical vibrational frequency multiply the enharmonicity constant. So this value is much smaller compared to this value, because this is minus 4 times, whereby this one only minus 2 times. That is why the positions of the peak for the overtone will appear on the left hand side to the fundamental transitions. Here are some of the comparison between the fundamental bands and also the hot bands. Fundamental transitions occur from the ground state to the first excited state, whereby hot band occur from the first excited state to higher energy levels. The intensity of the fundamental transitions is very high due to the large populations of the molecule at the ground state, whereby for the hot band, the intensity of this peak is big because the number of molecules at the large delta E between the vibrational energy level is low. And fundamental band will decrease in the intensity if the experiment is conducted at a higher temperature than the room temperature. But the hot band will start to appear in the spectrum as the temperature of the experiment increase. Thus far, we have learned the rotational spectroscopy and also the vibrational spectroscopy. In this figure here, you see two sets of lines. Okay, this set of the line is known as the excited electronic energy levels, whereby this set of the lines are occupying the ground electronic energy levels. Within the ground electronic energy levels and also the excited electronic energy levels, they have many lines which is corresponding to the rotational energy levels and also the vibrational energy level for the thick line. When we talk about rotational spectroscopy, it is referring to the transitions of the molecule which is activated rotationally at the ground electronic state and also ground vibrational energy level. The transitions occur in between the rotational energy levels, which is at the ground electronic state and also ground vibrational energy level. When we talk about vibrational spectroscopy, the stack of the vibrational energy levels are occupying the ground electronic state. So this thick line corresponding to the ground vibrational energy level, and this thick line here corresponding to the first excited vibrational energy level. Now we are continue to explore the rotation and vibrational spectroscopy, which will involve the transitions in between the rotational motions that are participate at the ground vibrational energy level and also the first excited vibrational energy level. Vibration rotation spectroscopy. As I told you before, in rotational spectroscopy, the transition between the rotational energy levels associated with the same vibrational level. For the pure rotational spectroscopy, we only focus on the transitions for the rotational energy levels which are occupying the ground vibrational energy level. Whereby in the vibration rotational spectroscopy, the transitions between the stack of rotational energy levels associated with two different vibrational levels, which are the ground state and also the first excited vibrational energy level. Vibrational transitions may be observed when the samples is in the liquid or the solid phase. But in order to observe the rotational transitions, the sample may need to be present in the gas phase. So they have the same requirement in order to observe the rotational spectrum, whereby The sample needs to be present in the gas phase. Only then we will be able to observe the rotational spectral line in the spectrum. This figure illustrates in more detail on the transitions or the energy levels involve the vibrational energy levels and also the rotational energy levels using the Morse potential energy curve. For the pure rotational spectroscopy, we only focus on the transitions within the ground vibrational energy level. So the transitions involve only among these few energy levels. But for rotation and vibrational spectroscopy, the molecules are rotationally excited during the vibrational transitions, meaning that the molecule will be excited vibrationally from ground state to the first excited state. And at the same time, the molecule will also be rotationally excited from one of the level in the ground vibrational energy level to the excited vibrational energy level, but in different rotational energy level. This figure illustrates the set of ground vibrational energy level and also the first excited vibrational energy level. And they are not drawn according to the scale, which the zigzag here illustrate the big gap between the energy level of ground state and also the first excited state. Within the ground state, there are a set of the rotational energy levels. And similarly, for the excited state, there are also a set of rotational energy levels. During the process of excitations, some molecules are rotationally excited in their vibrational ground state. This is what we have learned for the pure rotational spectroscopy, whereby the molecule will transit from J0 to J1, meaning that they are rotationally excited, or from J1 to J2, or from J2 to J3. But in fact, in the real world, if the sample is present in the gas phase, the molecule will be excited not only vibrationally from V0 to V1, the molecule will also be excited rotationally. But during the change of the vibrational quantum number from V0 to V1, the motion of rotation, it can be either excited, meaning that the delta J is increased by one level, or the molecule can also be de-excited rotationally with the change of the delta J, the rotational quantum number decreased by 1. Now, how are we going to quantify the amount of energy required for the transitions to occur, which involve a slightly complex transitions where both rotational motions and also vibrational motions occur simultaneously? We apply these Born-Oppenheimer approximations to quantify the amount of energy. The energy for the vibrational and also the rotational motions, they are very much different, whereby the separations energy for rotational levels is about 1 to 10 wave number, and for the vibrational level is about 1000 wave number. So you can see that 1010, the gap is actually quite huge. Besides that, the time scale for the vibrations and also the rotational motions are very much different. One rotation takes about 10 picosecond, which is about 10 to the minus of 11 second to occur, whereby for the vibrational motions, it is just about 10 femtosecond or 10 to the power of minus 14 second to happen. So the time scale and the energy difference for the two motions are actually quite different. Therefore, we can apply the Born-Oppenheimer approximations to quantify the amount of energy for the rotation and vibrational in a molecule. Approximation separates electronic motions from the nuclear motion. As a consequence of these separations, we can treat the energy of a combined state as a sum of the vibrational and rotational energies separately, whereby the total energy is equals to the energy of the rotational motions plus the energy for the vibrational motion. Therefore, the total nuclear energy of the combined rotation and vibration term, which is given as the S bracket rotational quantum number, comma, vibrational quantum number equals to the rotational energy plus the vibrational energy. And if you look into this in detail, it will consist of the energy for the rotational motions and the energy for the enharmonic oscillators, which is the vibrational motion. The total energy is just the sum of the vibrational and rotational energy. To make things easy, we can ignore the centrifugal distortion constant D and H in the rotational motions. But this is illogical. Why? So if we presume that D and H doesn't really play any role in the determinations of energy, then the equations can be reduced to this much simpler function. For the transitions to occur, the molecule has to fulfill or adhere to the selection rules, where the combined motions, which are the rotations and vibrations, the selection rules are the same as those for each of them separately, whereby the change of the vibrational quantum number can be any value. Yet, for the rotational motion, the change of the rotational quantum number is limited by either increase by one value or decrease by one value. The diatomic molecule may not have the change of the rotational quantum number equals to 0, but there are some exceptions to these rules. In other words, vibrational change must be accompanied by a simultaneous rotational change in the molecule. In the rotation and vibration spectroscopy, or we call it as the raw vibrational spectroscopy, it involves the fundamental transitions, which is the transitions that activate the molecule vibrationally from the ground vibrational energy level V equals to 0 to V equals to 1. We only focus on the transitions involved these fundamental transitions. In addition to the vibrational activations, the molecule will also be rotationally either activate or deactivate. If you refer to the blue lines transitions, it is referring to the change of the rotational quantum level from J to J plus 1. In other words, the blue transitions indicate the change of the rotational energy level to a higher rotational quantum number. So we call the molecule is being rotationally activated. For example, the transitions from J0, it can be activated to the vibrational quantum level equals to 1 and landed at J1, or from J1 to J2. So in this kind of transitions, it involves the two different types of the vibrational quantum level along with the rotational activations. For those transitions involved in the red transitions, they cause the rotational motions in the molecule to be deactivated, which means that the rotational quantum number will be reduced upon the excitations of the molecule from the ground vibrational energy level to the first excited vibrational energy level. The example of the transitions involved, for example, for this one, which is from J1 to J0, from J2 to J1, from J3 to J2, or from J4 to J3. So all the red transitions here involve the change of the rotational quantum number from J to J minus 1. The appearance of the peak caused by the deactivations of this rotational energy levels is known as the P branch. So rate transitions where J is decreased by 1 is indicated in the spectrum as the P branch, whereby if the molecule is being rotationally activated, then the bunches of the spectral line in the spectrum is known as the R branch. So you see here, R branch is the spectral line involve the blue transitions where the rotational quantum number increase by 1. This is one of the example for the appearance of the spectral line for this rho vibrational spectrum. We have the P branch and also the R branch. P branch is due to the rotational motions deactivations, whereby R branch is due to the rotational motions being activated when the molecule transit from the vibrational quantum level 0 to 1. Since we know that the energy of the rho vibrational motions can be quantified using the Born-Oppenheimer approximations, then what about the amount of the energy required for the activations to occur? So the amount of the energy required for the activations, we label it as delta S, and this amount of energy is the positions of the spectral line in the spectrum. So sometimes it is also labeled as bar-mu spectroscopy. If you consider only the transitions involved in the fundamental transitions, which is from V0 to V1, the vibrational transitions using the label J prime for J level in the V1 and J double prime for J level in the ground vibrational energy level. So for this slide here, we have the J prime to represent the final state of the rotational motions, and J double prime represent the initial state of the rotational motions. The positions of the spectral line can be obtained by the difference of the energy between the vibrational and also the rotational motions. Therefore, from here you will see that the molecule involve the transitions from the ground state of the vibrational motions to the first excited state for the vibrational motions. And at the same time, they will also involve the rotational motions, the final rotational energy level, and which is this one, and the initial rotational energy level, which is this one. So the difference between the final energy levels and the initial energy levels for each of the rotational motions and also the vibrational motions will give us the total amount of energy required for the transitions to occur to activate the molecule vibrationally, to activate or deactivate the molecule rotationally. So this is the amount of the energy required, and this is also the position of the peak in the rho vibrational spectrum. We can further evaluate the equations for the determinations of energy required to activate the molecule rotationally and vibrationally. So it will involve the energy difference between the ground and also the first excited vibrational energy level. This will result in the band center, which is equals to the hypothetical vibrational frequency minus 2 times the hypothetical vibrational frequency multiply the enharmonicity constant. It is given by the symbol of omega naught bar. So similarly, for the rotational part, we have to find out the energy difference between the initial state and also the final state. For the rotationally part, we can expand these equations and then we do some factoring. Eventually, it will give us the expressions as given here. In these equations here, we have to take note that the rotational constant B, the value is the same regardless it is at the molecule is at the ground vibrational energy level or at the first excited vibrationally energy level. Because we have already assumed that the molecule is rigid. If you still remember at the previous few slides, we assumed that there is no centrifugal distortion effect on the molecule during the rotational motion. So we can do the summations for the total energy due to the vibrational and also the rotational motions because we consider the Born-Oppenheimer approximation whereby the rotational motion is unaffected by the vibrational changes. We can have two cases here where it involves the delta J equals to either +1 or -1. In the case of delta J equals to +1, the change of the rotational quantum level, which it involves the activations of the molecule rotationally. So delta J equals to +1 equals to the final rotational energy level minus the initial rotational energy level equals to +1. And we substitute this one with J prime equals to J double prime +1 into the equations that we derived in the previous slide. So J prime is referring to the final state of the molecule and J double prime is referring to the initial state of the molecule. So after we substitute this J double prime +1 into the equations, and this is the equations that we will get for the transitions which involve delta J equals to +1. Similarly, for the delta J equals to -1, J double prime, which is the final state of the energy level, is equals to J prime +1. Okay, so in this case here, we substitute the J double prime into the equations given here. And this is the final solutions we will get for the change of the delta J equals to -1. We have to take note that all of the J value needs to be integer and the values range from 0 until infinity. These two equations can be conveniently expressed as the equations given here, where the delta S is equals to omega naught, the band center, plus 2b multiply m. The m can be the value of either +1 or -1, +2 or -2, or +3 or -3, and so on. Whereby the m, it gives us some hint about the number of peaks for the spectrum from the band center. So just now you have seen that this is the equations to determine the positions of the peak in the raw vibrational spectrum. Omega naught is the band center, which is at this position. So generally the raw vibrational spectrum will have a symmetry, okay, on the left and right, which is the P branch and also the R branch. And the center here is corresponding to the omega naught. Omega naught plus 2b m. For the first peak on the P branch here, we have the m equals to -1. So the first peak, the positions on the x-axis will be omega naught minus 2b. And the first peak on the R branch is corresponding to the m equals to +1. So the positions of this R naught 1 is at omega naught plus 2b. If you refer to this symbol here, it will tell you which branch is the peak referring to, and the symbol of this, it has some number as the subscript. The subscript will denote the initial rotational level. Okay, the initial rotational energy level. If it is R0, meaning that this peak is represent the transitions in the R branch. The R branch is involve the activations of the molecule rotationally, and the initial state of the molecule for this peak is from 0, meaning that the molecule will transit from V0 to V1. It will be activated vibrationally, and at the same time, the molecule will also be rotationally activated from J0 to J1. So the delta J is equals to plus 1. Therefore, it is categorized under the R branch. So similarly, for the second peak here, the positions, the value on these positions is equals to omega naught plus 4b, whereby the m is equals to plus 2. This is the second peak on the R branch. So it has the m value equals to plus 2. Plus 2 multiplied 2 will get plus 4. So the positions here is omega naught plus 4b for this peak here. And this peak is labeled with the symbol of R subscript 1. So the molecule will be activated vibrationally from V0 to V1, and at the same time, the molecule will also be activated rotationally from J1 to J0 at the first excited vibrational energy level. We apply the same to the P branch. In the P branch, the first peak here is given by the m equals to minus 1. So the positions, the value on the x-axis here is omega naught minus 2b. And the symbol given to indicate this peak is P subscript 1. P represents the P branch due to the change of the rotational energy level from J1 to J0, which is delta J equals to minus 1. And the second peak here, the positions is equals to omega naught plus 2b, but this is in the P branch, so the m value is minus 2, second peak on the P branch, so it is minus 2. So the position at this point is omega naught minus 4b. And this peak here corresponding to the transitions from V0 to V1, and at the same time, the molecule will be rotationally deactivated, where the delta J equals to minus 1. From J2, it will be transit to J1. So these are the labeling for each of the peak, and the gap between the P1 and R0 is equals to 4b. Okay, so another thing we need to take into alert is that we do not have P0. Then why we do not have P subscript 0? So you have to think about that. And then the peak separations, if you look into this spectrum here, the peak separations, they are equal. They have equal spacing of the spectral line. The value of the spacing is 2b. This is the consequence where we assume the molecule is rigid. So now you can answer, what is the separation between the two adjacent lines or the spectral peak? The spacing between the spectral line are approximately equal, between the R branch lines and between the P branch lines. So by assume that the molecule is rigid, then it allows us to determine the bond length of the molecule as what we have done for the pure rotational spectroscopy. And then the spacing between R0 and P1 is 4b. It is called the band center. The middle of the gap will be the fundamental frequency given by the symbol of omega naught. So these are the informations that we can gain from the raw vibrational spectroscopy. But will the molecule be rigid in reality? And this slide it summarizes the transitions involved in the P branch and also in the R branch, which at the same time the vibrationally motions is also being activated, and the bottom part here corresponding to the appearance or the raw vibrational spectrum for the molecule, which we assume the molecule is rigid. Before that, we have seen the intensity variation in the rotational spectrum. Then what about the intensity variation in the vibration and rotational spectrum or raw vibrational spectrum? The raw vibrational spectrum will show the same distributions of the intensity as what we have seen before, whereby the variations of the intensity for the rotational peak, they are actually determined by the equations as you will see here. So the ratio of the populations for the molecule at the initial and also the final state will determine the intensity of the peak. And the factors that are contributing to the determinations of this intensity is degeneracy, where it involves the 2j plus 1, and also the Boltzmann effect, exponent minus the energy difference between the two levels divided by the thermal energy. So basically, for the raw vibrational spectrum, the appearance of the maximum intensity peak will appear before the maximum peak, the degeneracy playing the major role in determining the increase of this intensity. After the maximum peak, the Boltzmann effect, which is the delta E between the energy levels, determine the transitions or the molecule which can occupy the energy level. Therefore, as you move up to higher rotational energy level, the number of molecules which can occupy that level is limited. As a result, you have a limited number of molecules which can be activated rotationally at higher J level. Therefore, we observe a reduction in the intensity of the spectral line at higher J transition. There are two spectrums here. This one is the ideal spectrum. It is called ideal because the peak separations are equally spaced. But in reality, the spectrum is slightly different, where we have the close-up of the spectral line for the R branch, and the spectral line in the P branch will space out as the J value increase. In reality, as shown by the HCl gas, the raw vibrational spectrum with the recorded positions of the spectral line as given in this table, if we look for the peak spacing between the neighboring peaks, then we get the value which is as given here. So the value of the rotational constant that can be calculated from the spectrum is not actually equal or not the same. Why are these systematically different in the value of the rotational constant? The rotational constant for the molecule at ground vibrational energy level and the first excited vibrational energy level, they are actually different. This is due to the bond length of the molecule are different when the molecule is at ground vibrational energy level compared to the first excited vibrational energy level. As the molecule excited from this level here to the first excited vibrational energy level, the molecule gain energy. When the molecule gain energy, it will be rotating at a faster frequency. When they rotate at a faster rate, it will cause the bond to be elongated. When the bond is elongated, then the rotational constant will become much more smaller. That is the reason why rotational constant at this level here, denoted as B subscript 1, will be much more smaller compared to the rotational constant at the ground vibrational energy level. Due to the variations in the rotational constant, the spacing between the spectral line in the R branch and also the P branch is no longer equally spaced. The variations of the rotational constant is also due to the vibration-rotation coupling effect. For a diatomic molecule, as the molecule vibrates more, the bond stretches, and it causes the average internuclear distance becomes larger for higher vibrational states. As a result, the moment of inertia changes, and this will cause the rotational constant, which is depend on the moment of inertia, will also be varied. Hence, the rotational constant will change depends on the vibrational quantum number. The rotational constant at different vibrational quantum level B can be expressed in terms of the equilibrium value B subscript E using the following equations, whereby BV is equals to BE minus alpha multiply the vibrational quantum number plus 1 over 2, with the alpha is the interaction constant, which is a small positive constant for each of the molecule. So the B is normally smaller in the higher vibrational state, and we can use these equations to find out what is the equilibrium rotational constant between the vibrational energy level, or if we want to find out what is the rotational constant at a particular vibrational quantum level, then we can find out their value if we know what is the BE and also the value of the alpha. Another factor which contribute to the variations of the rotational constant or to the variations of the peak separations is the centrifugal distortion. As the molecule spins faster, the bond is pulled apart. It will cause the change in the bond length to become longer, and hence the moment of inertia become larger. So the rotational constant in fact will depend on the rotational quantum level. We can find out the rotational constant using the equations given here, where we have the dE corresponding to the centrifugal distortion term, and BE is the equilibrium rotational constant. So when the above factors are accounted for, the actual energy for the raw vibrational state needs to take in considerations, which is arises from the difference in the rotational constant. By taking into the considerations of the different value of rotational constant at the excited vibrational energy level B1 and at the ground vibrational energy level, so we substitute this value into the equations to determine the energy required for the transitions to occur from J to J plus 1 or from J to J minus 1. So we get the R branch which is with delta J equals to +1, and P branch, which the delta J equals to -1. And these are the equations that we can use to determine the amount of energy required for the respective transitions. The simplify of the equations for the transitions to occur, or the amount of the energy required for the P transitions to occur, as well as for the R transitions to occur, are given by these two equations. So in general, the value of the B0 is greater than B1. Therefore, the line spread out as the J increases in the P branch, because it is a omega naught minus this bunch minus this bunch again. As we have the larger value of J, then the spacing or the position of the peak in the P branch will become much more far from each other. In the opposite, for the R branch, as the J value is getting larger, the peak separation will become closer to each other, because we have the omega naught plus this term and minus this term here. So we say that for the R branch, the lines bunch up as the J value increases, which leads to the convergence in the R branch. One of the example for the low vibrational spectrum for a real molecule, we will observe that the R branch will be bunched up, whereby for the P branch, the spectral line is spacing out. The next question is, can we determine the value of the rotational constant at the ground vibrational energy level and also the rotational constant at the first excited vibrational energy level from the spectrum given here? Yes, we can determine the value of the rotational constant at different vibrational energy level. We use the transitions with the common upper levels or the common lower levels to determine the rotational constant for each vibrational level. Meaning that if we would like to determine the rotational constant for ground vibrational energy level, which is the B0, then we will need to get the transitions that involve the terminations or the common upper levels that terminate, that landed at the same rotational energy level at the excited vibrational energy level. On the other hand, if we want to determine the rotational constant for the first excited vibrational energy level, we want to determine the B1, then we need to look for the transitions which involve from the same J level. Then there will be terminate at different excited vibrational energy level. This will allow us to determine the rotational constant at the first excited vibrational energy level. For example, R9 or R subscript 9 and P11 or P subscript 11 transitions use the simultaneous equations to calculate the rotational constant in the V equals to 0 state, meaning that find out the rotational constant at the ground vibrational energy level. And you are given the wave number of the transitions for R9 and P11 are respectively this value. So to solve this kind of problem, first of all, we have to know what are these transitions. What is the P branch? What is the R branch? Tell us. Which involve the delta J for R branch is +1. So the number here indicate the initial state. Therefore, R9 is equals to or corresponding to the transitions from J9 to J10 at the excited state from the ground vibrational energy level, whereby P11 is corresponding to the transitions of the molecule from V0 to V1 with the rotational quantum number J11 to J10. P branch is corresponding to the delta J equals to -1. So we have to draw out the levels of the energy diagram, or we call it as the Jablonski diagram. And with that, we can have a better vision. It will visualize what is the transitions involved and what do we need to find out. And these are the stacks of the energy levels, or we call it as the Jablonski diagram. The blue color transitions corresponding to the transitions from J11 to J10. So this is the P11, which is the delta J equals to -1. While the red transitions is the R9, which involve the J9 to J10 with delta J equals to +1. So this stack of energy levels corresponding to the ground vibrational energy level, and this stack of energy levels corresponding to the rotational energy level at the first excited vibrational energy level. So by having this diagram, now you can see that the difference between this point and this point here, okay, is something that we can find out from the information given. We know that for these transitions, it required an amount of energy of 2099 wave number, whereas for these transitions, it required 2179 wave number. So the difference between these two is actually equals to the value of the energy at this level minus this level. So how to find out the value of energy in the rotational motions? We use the equations Fj equals to Bj j plus 1. In other words, R9 minus P11, which is the energy required for the transitions of R9 and P11, these transitions and these transitions, their difference is actually equals to the difference of energy between this level and this level. Therefore, we have the F11 minus F9. Okay, so we find out the F11 R9 minus P11 equals to F11 minus F9. What is F11? F11 is the value of the energy at J equals to 11. And it is equals to B11 multiply 11 plus 1. So we have B11 multiply 12. And this B is referring to the rotational energy level, which is this B is referring to the rotational energy at the ground vibrational energy. So this B is the rotational constant at ground vibrational energy level. Therefore, we have the B subscript 0. Similarly, F9 is equals to BJ9, which is J is 9, and then 9 plus 1, we will get 10. So we have 9 times 10 times B0. The difference between these two levels, F11 and F9, is equal to the difference between the energy required for these two transitions. So from here we can find out what is the B0. If we take into considerations the effect of centrifugal distortion in these equations, where it determines the amount of energy required for the transitions to occur, Then we will have omega naught plus 2bm minus 4dm cubed. And you have to keep in mind that the m is referring to the number of the spectron line from the center band or the band center. And the value of b is about 10 wave number, but the value of the d is only about 0.01% of the value b. Therefore, we can neglect the value of this centrifugal distortion constant in the determinations of energy required or the positions for the spectral line in a spectrum. But we cannot ignore the value of this anharmonicity constant. Anharmonicity constant, the value is embedded in the band center. So it affects the positions of the band or region if we neglect the anharmonicity constant. The figure shows the carbon monoxide vibrational spectrum took at low resolutions and also at high resolutions. At low resolutions, we can observe the peak splits into two bands with separations approximately 55 wave number. At the high resolutions, then we were able to observe that these two bands split into two sets of almost equally spaced fine lines due to the rotational transitions in the sample. Here is another example to determine the rotational constant and also the band center omega naught. So from the spectrum, we can obtain the rotational constant by having the informations obtained from the spectrum. So we can determine the rotational constant and also the band center. If the rotational constant for carbon monoxide is this value and the band center is this value, so the band center, which is also the fundamental vibrational frequency for carbon monoxide, the fundamental vibrational frequency can be determined using this, can be calculated using these equations. And in addition to that, we also be given the first overtone. The first overtone we can calculate through the equations here as well to determine the hypothetical vibrational frequency and also the anharmonicity constant. So meaning that if you know what is the band value for the band center, then this is equal to the frequency for the fundamental transitions. By knowing the frequency of the fundamental transitions, and if you know the value of the first overtone, the energy required, you can further determine what is the hypothetical vibrational frequency as well as the anharmonicity constant. Similar to the pure rotational spectroscopy, if one of the atoms in the molecule is replaced by isotope, then the presence of the isotope can be traced with the appearance of a peak which is in pair to the molecule which is not substituted with the isotope. So in this example here, HCl35 and HCl37 are both present in the sample. Therefore, you see that at a very close positions, there are two peaks appear, and these two peaks, they are pair, and the height will reflect the natural abundance ratio. So usually we have this one which is much more higher compared to this one, and the higher one is the HCl35, and the lower one is the HCl37 with the ratio around 3:1. So if you see two peaks which appear at a very close position, it tells you that in the sample it contains isotope substituted molecule. So this is the actual IR spectrum where we have the y-axis corresponding to the percentage of transmittance, and the x-axis is the wave number. Similarly, this one is also the IR spectrum for hydrogen chloride. So in this case here, the IR spectrum, you can see the presence of these very fine lines. The fine line here is corresponding to the gas phase of the molecule, where it performs the activations of the rotational motions. Therefore, we can observe the appearance of these fine lines due to the rotational activations. So we have the rotation vibrational spectroscopy in this figure. You can have both transmittance and also the absorbance peak. But the transmittance spectra, it can provide a better contrast between intensity of strong and weak bands compared to the absorbance spectra.